Okay, so let's give you a quick review for previous class. We introduced 4 different kinds of atomic diffusion mechanisms in crystal lattice. The first one is ring mechanism. That means the diffusing host atom exchange the site with nearby or surrounding host atoms together or move together simultaneously. So usually that will cause the higher lattice distortion. So that means the energy barrier to these diffusing atoms is high. So you only can observe this kind of phenomena in high temperature. And the second one is the vacancy mechanism. That means the diffusing host atom exchange or jump into surrounding or nearby vacancy site, and which leads the diffusion happens. So in this kind of case, the self-diversivity of the host diffusing atom is proportional to atomic vacancy fractions and diversivity for vacancy and correlation factor. And you know that it will also proportion to exponential vacancy formation energy plus the vacancy migration energy. So actually, that's the other diffusing mechanism is similar with the vacancy mechanism, which we call it the interstitial mechanism. Because in this case, actually the diffusing atom, there's much self-interstitial defect nearby the diffusing atom. So the self-diversivity for this diffusing atom is proportional, equals to the atomic fraction for these interstitials, diffusivity for this interstitial, and the correlation factor is similar, right? The vacancy mechanism actually is there's much vacancy nearby the diffusing atom. It's something similar. So it's much. This will help you to remember what's the relationship between the diffusing atoms and even the vacancy atomic fraction of vacancy or the atomic fraction for the interstitials. Okay, so based on these results, you know the self-diversivity of diffusing atoms through the interstitial mechanism is proportional to what? This is the interstitial defect formation energy proportional to this is proportional to the migration energy of these interstitials. And the third one actually is the interstitial mechanism. Actually, the diffusing atoms is solute atom located at interstitial site with smaller size, right? And the diffusivity and also these interstitial diffusing atoms or solute diffusing atoms diffuse through interstitial size. So the diffusivity is proportional to only the exponential minus migration energy of these interstitial atoms, diffusing atoms. So this is the roughly introduction. We already give you a brief review for 4 different kinds of diffusing mechanism in crystal. And next, we are going to show you the other case and emphasize on vacancy mechanism part. The case we just mentioned for the vacancy diffusion mechanism is we have a pure materials. All the host atoms are the same types or kinds of atoms, and we discuss the self-diversivity of these host diffusion atoms through this through vacancy, through exchange, jumping into vacancy site, right? But how about if you dope some solute atoms into these materials, and these solute atoms will replace or locate at substitutional site? Can you explain or try to get the diffusivity for this solute atom at substitutional site through vacancy diffusion mechanism. So this case we call it is a vacancy mediated solute diffusion. That means the solute atom at substitutional site, but it will diffuse through exchanging or jump into vacancy site. And can you formulate the diffusivity for this diffusing solute atoms? So let's following slide is going to show you how to get this diffusivity for these solute atoms. So in this case, we call it as a vacancy mediated solute diffusion, and we take the FCC structure as an example. So the black circle means the host atom, and probably you will dope some solute atom to replace or locate at substitutional site. And we assume there's a vacancy nearby. We call it a V means the vacancy site. So here, in order to get or obtain the diffusivity for this solute atom, first of all, you need to figure out how many types or kinds of atomic jump rate show in this case. So let's a quick review. The atomic jump rate in specific direction is associated with the bond strength, the reduced mass, and energy barrier, which due to the lattice distortion. So based on this, because there's a solute atom, the solute atom means it's a different kinds of atoms compared to the host atom. So the bond between the solute atom and host atom, or solute atom with the vacancy, definitely different, and also the mass will be different, reduced mass will be different. So here we got three different types of or kinds of jump rate need to be considered. The first one is the jump rate you need to consider is the solute atom jump into the vacancy side. We use the gamma prime SV, use this double arrows to represent this kind of jump rate is the solute atom jump into vacancy site. And the second one is we call is a host atom but surrounded neighboring a solute atom, and we label it as a green. It jump into a vacancy, so we use this to represent the atomic jump rate of the surrounding host atom jump into a vacancy site. And the third one is the host atom jump into a vacancy, so it's a jump rate of the host atom jumping into the vacancy site. And due to the so we need to consider three different kinds of jump rate, and need to think about that which jump rate is faster, which one is slower, because the slower one will be the limited step for diffusion process, right? So here we make a very important assumption. We consider there's an attractive interaction between the solute atom and vacancy. So there's an attractive interaction. So that means there must be a negative binding energy between the solute atom and the vacancy. So as you know, if there's a negative binding energy, so the migration energy term, we need to modify it. We minus the extra term. So the total energy for solute and vacancy, jumping between the solute and vacancy, the total energy will be lower. And as long as this lower, then you can expect the atomic jump rate, gamma SV, the solute vacancy jump rate will be this smaller, so this will be faster or higher. So compare with this one, a jump rate is higher. So we can discuss, this the other important assumption is compare with this one, the host vacancy jump, the energy will be compared to relative to this one will be higher compared to this one. And if you got the higher energy turn, then you will get the lower atomic jump rate. So now we know there's two important assumptions. There's a negative energy, attractive interaction between cellular and vacancy, so they can be considered as a pack, a group. And the second assumption is the possibility or the jump rate of host atoms jump in vacancy is quite small or quite low. So you can, based on these two assumptions, and you can make there are two possible cases here we are going to discuss about is based on the jump rate, the host vacancy jump rate is always is the smallest one, but the cellular vacancy jump rate is higher than the near the host neighboring cellular atom jump into the vacancy. So this one is highest than is the host atom is a neighboring cellular atom. Is a host atom nearby the cellular atom jump in vacancy one is this one is higher than this one, much higher than this one, and also this jump rate is much higher than the host atom jump in vacancy. And the second case will be switch the order between the host atom nearby the cellular atom jump in vacancy. One is higher than would be the cellular atom jump in vacancy, and the slowest one is the host atom jump in vacancy. So we are going to investigate, based on these two different types of cases, how to formulate the diffusivity for this cellular atom. So let's move to the first one. Yes, based on the atomic jump rate, first case is this one, cellular atom jump in vacancy, the jump rate is highest. And next will be this one, is the host neighboring cellular atom jump in vacancy, and the slowest one is the host atom jump in vacancy. So don't forget, the purpose here is we are going to formulate the diffusivity for this cellular atom. So we need to find which one is the limited step to control this kind of diffusivity for the cellular atom. So I draw figures to help you can have some idea about which jumping process is a limited step to control the diffusivity for this cellular atom. So as we mentioned, the cellular vacancy the jumping process between the cellular and the vacancy is highest, right? So probably after 1,000 times jump, then probably there was one jump between the host's neighboring cellular atom jump in vacancy. So that will become, but as you know, even the jumping rate is quite high, but this kind of jumping process has no contribution to the diffusion of the cellular atom, right? Because they just jump back and forth. But after 1,000 times of jump, there's a one-time jump between the host's neighboring atom jump into the vacancy. So the vacancy will become here, and the host neighboring cellular atom will become here. And next step probably is also is the jumping between the cellular atom and the vacancy. Then after 1,000 times of jump, There's probably one time jumping between what? Between the when the vacancy jump to here, then there's probably one time jumping from the host enabling Cellular atom jump into vacancy. So that will result this kind of vacancy will become here, and the host enabling Cellular atom will become here. Then, as we mentioned, there's also 1,000 times of jumping between the solute and the vacancy. So next, probably one time of jumping between what? Probably will be like becomes here. So you can find that the solute atom diffuse from here to here, and the limited step actually is the what? Is the jumping between the host enabling solute atom and the vacancy, jumping into the vacancy side. So this will be the limited step. So when you try to write down the diffusivity of this solute atom, then the rate limited step will be the solute will be the host enabling solute atom jumping into the vacancy side. So the diffusivity for the solute atom, self-diversivity for the solute atom binded with vacancy, as we mentioned, is considered a negative binding energy between them. So it's a bandwidth energy with proportion to what? It can be expressed equals to gamma prime is the atomic jump rate between the host enabling solute atom jumping in between the host solute atom and the vacancy. And also we need to times the alpha A. Alpha A here is a geometry factor, which is highly associated with the crystal structure and for example, the F, the correlation factor, the diffusion mechanism, all the parameters will be put into alpha A here. But the most important thing is the diffusivity for this solute atom is controlled by the jumping rate between the host enabling solute atom and the vacancy. And next, we are going to try to write down the diffusivity for the solute atom instead of the binded one. Binded actually is you consider as a group, right? So when we try to write down the self-diversivity for the solute atom, the idea would be that you need to consider also the atomic fraction for the vacancy solute you can observe in your materials, and also times the diffusivity for this solute vacancy pack. And regarding to atomic fraction for this solute vacancy, then we use the PV is a probability to find the vacancy at the thermal equilibrium condition. But this is a probability to find the vacancy, right? But this one already is considered as a group. So we need to times, because you have a vacancy, right? There are 12, because this is FCC, there are 12 nearest atoms, solute atoms possible is surrounded it, right? So we need to times 12 to represent the total probability to find this pack, a solute vacancy pack. Okay, so this is a total atomic fraction for finding this pack. So we take this to substitute this term, and after arrangement, then you can get the self-diversivity for this solute atom is proportion to the atomic jump rate between host enabling solute atom and vacancy, and also the probability to find this vacancy, this vacancy bind with solute will be proportion to exponential minus vacancy formation energy and also the binding energy between the solute and vacancy. So this term will be the probability to find a vacancy binded with a Cellular atom. So this is a case 1, right? And next we are going to introduce the case 2. Case 2 actually, the jump rate between the host atom and vacancy is the slowest one, and the fastest one is the host neighboring Cellular atom and the jump into the vacancy. This is the fastest one. And next will be the Cellular atom jumping into the vacancy. But as you know, this one is a fast one. So next step, when this one is fast, so move here, so vacancy will be here. So the host neighboring Cellular atom will be moved here, vacancy will be here, right? And the vacancy will be some kind of surrounding, a circling by this kind of jumping process. And this jumping process actually is nothing, has no contribution to the diffusion of the Cellular atom, right? So which jumping process will be the limited step to drive this diffusion of the Cellular atom? So let's take these figures. As we mentioned, the fastest one will be the host enabling Cellular atom jumping into the vacancy. So that will cause the circling effect. The vacancy will be circling around the Cellular atom and has no contribution for the diversivity or diffusion for the Cellular atom. But after probably 1,000 times of jumping of host enabling Cellular atom and vacancy, so probably 1 times of jump between the Cellular atom jump into the vacancy. So the figure will becomes the Cellular will become here and the vacancy will become here. And next, there probably 1,000 times of circling stuff between the host enabling Cellular atom and vacancy. And this jumping process has no contribution to the diversivity for the Cellular atom, right? And after probably 1,000 times jumping, and there's also 1 time of jumping between the Cellular and the vacancy, then you can observe the Cellular becomes here. So from this, based on these figures, you know the diversivity, the diffusion, you observe diffusion happens on the Cellular atoms because the jumping process between the Cellular and the vacancy. So the limited step would be the jumping process between the Cellular and the vacancy. So when we write down the diversivity for this Cellular and bind it with the vacancy, as we mentioned, will be proportional to the atomic jump rate between the Cellular and the vacancy. For this case, will be the limited step because of Cellular, and alpha B is also the geometry factor related to the crystal structure and diffusion mechanism, correlation factor, and so on. So in this case, we want to write down the self-diversivity for this Cellular atom, and can be expressed like atomic fraction of the Cellular and vacancy you can find in these materials, and also the diversivity for this Cellular vacancy pack. And the probability term, yes, as we mentioned, the PV is the probability you can find the vacancy, right? But in FCC, there's 12 nearest atom possible size, so you need to times 12 to get the expression for the probability to find this Cellular vacancy pack. So you can write down this. You can get the diversivity, self-diversivity for this Cellular atom can express like this. So you can get, in this case, the diversivity actually is controlled by the atomic jump rate between the Cellular and vacancy, and also explanation term part energy is limited by vacancy formation energy. So you need to have a vacancy, and the other one is the the vacancy need to bind it with solute atom is a binding energy term. Okay, so let's give you a quick summary here. If your material is not a pure material, and the diffusion process is also vacancy mediated diffusion process, that means then you want to know the diffusivity for this solute atom at substitutional site, then this will be proportion to the with the the diffusivity for this solute atom binded with vacancy, and also the probability to find the vacancy solute pack. So you can write down like express like this. So atomic jumper rate actually will be related to the migration energy, and the rest of part is the vacancy formation energy and also the binding energy between the vacancy and solute atom. And the gamma prime, depending on what kind of case we talk about, so it will be slightly change with the migration energy term. Okay, so let's move to the second part. The second part is we are going to talk. The case we give you here is more like the metal materials, right? So now we need to move to the atomic diffusion in ionic solids. And in this part, the diffusion mechanism actually is limited by the vacancy mediated vacancy mechanism. So first of all, we need to know how many types of vacancy defect be observed in ionic solids. Then we can determine, or we can have idea how the ions jumping through vacancy, and know the vacancy. So we can get the self-diversivity for specific ions, right? And next we are going to show you there are two different cases: extrinsic and non-storage geometry. How to modify the diversivity of the ion, specific ion you are interested in. Okay, so the most important thing is get the self-diversivity for specific ions. So first of all, you need to know in ionic solids, we usually have the cation and anion, right? So what kind of there are two possible usually observed vacancy defect, and the first one is we call a Ch4 defect. Ch4 defect is there's a cation and an ion be removed from materials, so that would cause a pair of cation and an ion vacancy. A pair of that means the numbers of the cation vacancy and ion vacancy will be the same. We got a pair of cation and an ion vacancy. This kind of defect, vacancy defect, we call it is a Ch4 defect in ionic materials. And the second one is the vacancy defect. A vacancy would be a pair of cation self-interstitial and the vacancy and its corresponding vacancy. Take the silver bromide as an example. You can observe the silver atom was at here, right? And it be removed or jumping to the other interstitial side, serving as a self-interstitial defect, and left a vacancy, an ion vacancy here, and the pair of this cation interstitial side and the anion vacancy, we call it as a Frankel defect. So we do have two different types of vacancy associated defect, because both of these two defects will generate the vacancy, were correlated with the concentration of vacancy of the specific ions. Okay, so let's give you, and first of all, please before we move to next slide, probably you can think about which energy barrier is higher. To get the formation energy for Ch4 defect and formation of Frankel defect, which one is higher? Ch4 defect, right? Because you need to remove a pair of cation and anion. So the formation energy for Ch4 defect is higher than Frankel defect. And this is an example. We have materials here, solid materials here. As long as you remove a pair of cation and anion, then you will generate a pair of Ch4 defect. And in order to identify which ions locate at which site with what kind of charge and charge state, we need to learn the notation. Grover-Ring notation here. And the A here, you can use if we talk about the ion, you can put the atoms. Or if we talk about the vacancy, you use the V to put here. So like here we talk about the V, right? It's a vacancy. And the right bottom part actually is the site. Means the atom or the vacancy is you want to point out is located at which side of the atom. And the right upper portion here is labeled related to the charge state. Is if it is with one positive charge, then we use the positive here, or use the black circle here. If it is carried with negative charge, we use the either prong here, or use a prong means the negative charge, and carry with the electrons. And if you use a cross, means these atoms with no is neutral. Okay, so it's not either carry a positive or negative charges, and compared to it was, so it's a neutral. Okay, so let's give you some examples. We grab some FCC structures, including the ionic materials belongs to FCC structures: potassium chloride, sodium chloride, and silver bromide. And you can observe this is a double FCC structure here. And how to now you have some idea about the we do have to defect to generate or produce the vacancy, the vacancy for the ions, right? And next we are going to show you how can we get the diffusivity for specific ions in these ion materials. So first of all, we talk about is the sodium chloride FCC structure with a FCC structure, and with if you let a Ch4 defect happens in this potassium chloride. So in order to get the self-diversity for potassium ions or the chloride ions, first of all, you need to know, don't forget, it's a quick review. The self-diversivity for specific ions or atoms is proportional to the atomic fraction for this vacancy, diffusivity for this vacancy, and also the correlation factor F. So basically, as we know, if it is under the thermal equilibrium condition, the vacancy atomic fraction for the vacancy is equals to vacancy exponential minus vacancy formation energy over kT, right? So let's take a look on this potassium chloride ions. Before you observe there are Ch4 defects exist in this material, so it was the potassium ion located at the potassium side with neutral charge, because it was the charge didn't increase or decrease, right? So it was the potassium ion located at potassium ion site, and the chloride ions located at chloride side, so it's perfect before we observe some Ch4 defect, right? If now there's a Ch4 defect formed in this crystal, then you observe the pair of vacancy form, right? Would be the what? We can observe a pair of vacancy VK prime and VCl dot. Prime is because the potassium, it was carried with hole, right? So the vacancy will be a negative charge. And chloride actually is a negative, carried with electron. So the vacancy, as long as the chloride left be removed, so the vacancy should be carry one positive charge. And the rest of part also the potassium ion at potassium side, chloride at chloride side. In order to simplify this equation, some people will use this to substitute to replace this expression. Use a new none equals to the formation or formation of pair of vacancy for VK prime and VCl prime or dot, right? And don't forget the formation of this both this vacancy, cation vacancy and anion vacancy, the numbers should be the same, right? Always generate as a pair of the cation vacancy and anion vacancy. So based on this equation, you can formulate the K equilibrium, can be write down the atomic fraction of Vk times the atomic fraction of Vcl, and this will be equals to this is Ch4 defect formation. So this energy term will be the Ch4 defect formation energy. So in order to explain this more, so we just use the A, will convert it to C and D, this as an example. And the rate constant with the forward will be K1 and the back will be K2. So you can easily write down the K1 times the concentration of A, it will be equals to K2 times the concentration C and D. And this is, you can, if you write down to express based on the energy term, will be K10 exponential energy barrier. So A becomes to CD, right? So energy barrier will be minus E1 over KT. And K2 is this direction, right? So the energy barrier here will be E2, right? So what's the K equivalent is the K1 forward rate constant divided by the backward constant. So you get this, right? So you substitute CD over A, so you A move to right-handed side and K2 move to left-handed side, so you got the K1 over K2. So if you divided this, you can get what you directly divide this with this. So you got the energy will be becomes to proportion to minus E1 minus E2. So E1 minus E2 actually is the energy barrier we're talking about. So that's why based on this equation we can directly get this atomic fraction, vacancy atomic fraction, the vacancy fraction for Vk times the vacancy fraction for Vcl equals to what? Exponential. This relation, this equation is explain the formation of Ch4 defect, so it will be the Ch4 defect formation energy. Okay. So based on this, we get this idea, right? And the other very important thing is don't forget, based on the neutrality, so electrical neutrality, the numbers of Vk will be equals to the numbers of Vcl, right? As we mentioned, the formation always as a pair, as a unit, a pair of cation and anion vacancy. So you know based on this equation relationship, Vk equals to Vcl. So you substitute into these directions, and you can get the Vk, the atomic, the vacancy fraction for Vk and Vcl will be exponential, will be equals to exponential Ch4 defect formation energy divided by 2 kT, is 2 here, bottom part. So now, the purpose here, we want to get the self-diversivity for specific ions. Here is for K and Cl. You need to, first of all, you need to know the vacancy fraction, and then you get the F and also the vacancy diversivity for the vacancy, right? So let's try to formulate the diversivity for this cation dk star. The K here, K is a small black atom, right? This atom diffused through vacancy, Vk, right? So you can write down is the vacancy fraction for K, and the diversivity is the potassium ion diffused through Vk in terms of correlation factor F, and we use the G, means the G actually is because we talk about the ion materials, so that involve some different types or different kinds of mechanism. Some people so we'll put a G here. Okay, so based on this, as long as this is not FCC, so you also need to modify some coefficient, some parameters. So put all the coefficients into G. Okay, but the most important thing is you need to know the self-diversivity for potassium ion is proportional to XVK dk, the potassium diffused through vacancy Vk and F. And based on this, and the same thing happened in the DCl, diversivity for this anion Cl will be the vacancy fraction for Cl, and diversivity for this chloride ions diffused. Chloride ions will be the larger one diffused through this VCl. So as long as you get this one, you can try to formulate this one. Okay, so don't forget, I give you some review here. For previous slide, actually we get if it is FCC vacancy mediated diffusion, you got these results, right? So we just copy the parameters here, but the most important thing here is what's the XV. XVK is here, so is the Ch4 defect formation energy. So we separate them into the entropy and enthalpy term here. And next will be the diversivity for the potassium ions. Will be the what? Potassium is a migration energy, so you also separate them in entropy and enthalpy term. So it's similar, right? It's a formation energy. But here in the vacancy one is in metal part, actually it's a vacancy formation energy, and here we use the Ch4 defect formation energy and the migration energy and also migration energy, and you just copy the parameters here. And as we mentioned, this is ion material is double FCC, so some a correlation factor or some diffusion mechanism jumping process is a little bit slightly different, so we put the G here to modify it. And talk about the anion part is the same thing, right? You need to write down the vacancy fraction for Cl. Cl is Ch4 defect formation energy divided by 2kT, so we also separate them into entropy and enthalpy term. And diversivity of these chloride ions diffused through vacancy VCl, so it's a vacancy migration energy term, and the A is the anion diffused through the vacancy, means that, and also you put a G here. Okay, so the most important thing is you need to formulate the explanation part and also this one. And don't forget, as long as you deal with the ionic materials, you could put a G to modify this part will be you can consider as a different crystal structure if the ionic is not FCC. So you need to based on the coordination number difference, so you need to modify them, right? So just put all the coefficients here related to different crystal structures, and also different correlation between each jumps, something like that. Okay, so based on this, we also successfully to separate them into two terms. The first one is temperature independent term, and the second term is temperature dependent term, and the energy barrier for the cation or anion to overcome will be included the migration energy. Either the cation jump into the vacancy, or the anion jump to the vacancy, plus the Ch4 defect formation energy divided by 2.